What's the plan for today's expert session? So in the beginning we will talk about the simplified principle of the Smart Fusion in general to get everyone on board. Then we will also talk about the Smart Fusion replay feature, how it works, what's the idea of it, and after that we will also have a closer look onto OT data that we have recorded on our M290s and compare the data with it. All in all, we will also have a look on the qualification of AM components and then have a short conclusion about the complete Smart Fusion replay feature. Let's start with the simplified principle of the Smart Fusion. All starts with preparing the job within EarPrint. So we load the data into EarPrint, we prepare the CAD files, we assign a certain exposure set, and with that we also set up the target wear value. If you need more information for the target wear value, I would refer to the training that we have because I cannot go into detail now. But in the end, what we do is when we send the job to the machine and we record the job with our Exposure OT software solution with the camera, we receive several images which show the thermal behavior of the process itself. And when we look on the data, we see that in the part statistic that is created, we see that we have a certain level that is achieved in the gray values. And with that, when we have a certain target gray value, we will try to always match the target gray value with the signals that we see or record within the OT. In that case, I have an example where I show an overheated area on a part. And what now Smart Fusion is doing is it uses a PID controller to match, to reduce the heat emission that we record with the camera to the certain target gray value and to avoid overheating in that area. With the PID controller, we could generate multiple images across the complete job. So after a job, for example, we have more than 4,000 laser correction images, and then we will have the data in the end with all the information how the laser power was reduced, in which area, in which layer. So now let's come to the Smart Fusion replay feature. So in the end of a Smart Fusion job, we have more than thousands of different laser correction images that we can now use to rebring them into the EarPrint. So the idea is we use the information that we gathered during the process, so the initial and master process with Smart Fusion, and take the stack of images and bring that back into EarPrint to directly modify the laser power in that area where it's needed. Maybe just some additional notes to that. And to clarify what Smart Fusion replay considers and whatnot. As you've seen before, the laser correction that is made by Smart Fusion, so all the laser correction images are considered for the Smart Fusion replay job. So when you bring that back into the job, into EarPrint and rebuild it, this information is already there. In addition, we also gather in forefront the information about the laser linearization of the master machine and bring this also back into as information to the job preparation to ensure that even when you change the laser linearization or you have a degradation in the laser itself, that the same laser power will be on the same position as before. Okay, now let's come to the M290 OT Smart Fusion comparison. So what we did is we took the Smart Fusion job, we recorded the OT data, and afterwards we compared the OT data from the Smart Fusion job and the Smart Fusion replay job. So that you can follow me and understand what I'm talking about in the following some minutes, there will be some metrics I will mention. So in general, with the OT data, we will see the mean gray values that we have during each job for the layer and the parts. In addition, we have also metrics that is called the process stability. It's easy calculation between the standard deviation across over its mean gray value. So it could be part dependent, but it can be also layer dependent. And in addition, we also have another metric that's called the relative difference to the reference. So what we do is we have the Smart Fusion job, so I call it master job, that is the nominal job, and we compare the next Smart Fusion replay job to it. So we calculate the difference, and then we calculate the relative deviation to this nominal job. In the end, we receive something like percentage deviation to its nominal job. Let's have a look on the Smart Fusion replay results what we did on the M290. So when we compare now all the OT data that we have recorded during the build process, so the Smart Fusion job, which is purple in the line, and the other two Smart Fusion replay jobs, we see nothing. So the data is comparable, equal. What we do next step is that we create the relative difference to the reference. So in this graph that we provide here is we show on the y-axis the mean gray value, but with the metric relative difference to the reference. So the nominal job is the baseline, and the other two jobs we are comparing to it. And what we see now is that the difference between those jobs is quite small. So the relative difference of the Smart Fusion replay jobs are nearly equal to the Smart Fusion job itself. It's within plus minus 2%. Even we have another metric. It's a method to bring all that information into one image. What we do is we calculate the mean deviation across all layers and bring it into one image, and that's displayed on the next two images that I will show you. And what we see is that the maximum deviation that we have here for the mean gray value is within 0.4% across all layers. Let's have a closer look on the process stability. So as I mentioned before, we have the process stability, which is the standard deviation over mean. It shows us how stable a process is in each layer. And even when we compare it like before, so we have here on the y-axis the standard deviation over mean, so the process stability, and the layer count on the x-axis, we see nearly nothing, and all jobs are comparable, equal. When we zoom into it, we still see no difference. And that's why we took, again, the metric, the relative difference to the reference, where we have the baseline, the nominal job, and we compare the Smart Fusion replay jobs with it. And so we can see that the Smart Fusion replay jobs are within, in the beginning, 8% deviation. So we have a small deviation in the beginning, but within a longer period of time, we see that difference is quite small, and it's even smaller and the process is more stable, like the Smart Fusion process itself. So what we see is the Smart Fusion replay result is even better than the Smart Fusion original job. We can again look on the final images where we stack all the information that we have layer-wise into one image. So what we did again is, for the process stability, we stack all the information, so all layers, and calculate for the process stability, for the relative difference of the process stability, a final image which gives us a good overview about the process on each part location. And what we see here is again that the complete process across the build platform is within 1 to 3%, and on certain areas, starting with layer 100, it's even more stable than the original job. And now I will hand over to Michi, who will give you some insights into the qualification of AM components.
So why is Smart Fusion replay a must? In regulated industries, for instance, the medical device sector or aerospace, there's always authorities that have the power to shut down your production. So these authorities have the implicit need to understand why additive manufacturing has certain tolerances or variables, and they need to understand what needs to be controlled in what manner, and therefore the need for locking down process parameters is of utmost importance to them. So how does a qualification today work? I will give you a simple explanation and go of course then later to how that translates into additive, based on a standard installation qualification, operational qualification, performance qualification. If you buy, for instance, a washing machine, get it installed at your home. So let's assume you buy a washing machine at your local dealer, whether it's MediaMarkt or Best Buy, doesn't matter. A service technician comes and is having the washing machine ready to be installed at your site. He needs to check whether the floor is even, whether you have water, whether you have access. We call that an installation qualification. During the installation qualification, it is technically checked whether the washing machine can be installed at your facility and all the auxiliary supplies are available for your production. Well, a washing machine, can that be translated to a 3D printer? Of course it can, because there's also installation guidelines for an AM machine, and also those need to be fulfilled. In the next step, during the operational qualification, it needs to be verified that the machine is working as intended under normal operating conditions. For instance, all the buttons, the dials are working, the doors opening and closing and locking, the water is flowing inside, the machine can reach its absolute temperature. This is exactly the same with additive manufacturing. In additive manufacturing, you have a 3D printer with a lot of different variables that need to be controlled. And those controls are being checked typically during the operational qualification. So that the machine can reach its nominal laser power, certain scan vectors, trajectories can be scanned, the layer thickness is correct, and so on and so on. So it's nothing different in a, of course, simplified term than operational qualification of a washing machine. During the performance qualification of your washing machine, the simplest test is you take dirty laundry, put it into a washing machine, and you get clean laundry out. This is performance qualification. You check that the intended use of your component, of your system, is meeting the requirements. So in additive manufacturing, it's no different. You have a component for an intended use to be put into a human being as an implant or as a component going into an aircraft. It has requirements such as mechanical requirements, geometrical attributes, or whatever. So those need to be fulfilled, and they are tested against certain standards during the performance qualification. Of course, for additive manufacturing, there's a lot more variables that need to be under control when going to a production. And therefore, a lot more checks need to be performed. Checks, for instance, on mechanical property, consistency. You check the durability, the strength, the hardness, all different variables or mechanical properties that define your component. You check that the accuracy and the tolerances are met. You check that the quality of the surfaces are okay. You do functional testing of surfaces that are acceptable or not. And you check, of course, for the material integrity of your components. So during a qualification, typically what authorities ask is that you identify critical process variables. Those critical process variables need to be tested against their natural and standard fluctuation as well as worst case conditions. So what you typically do is you do process sensitivity testing. So you check the operational limits. You see what is actually potentially going wrong in your system or can go wrong, and how can you identify those and test against your requirements. So for instance, let's take the most obvious process parameter that has a dramatic impact on your mechanical properties, as well as surface roughness or geometrical accuracy, which can be determined as the laser power. So typically in additive manufacturing, what you do is you vary the laser power against certain nominal values. For instance, you have 400 watts as your standard process setting, and you see what is the effect if I subsequently reduce in, for instance, 5% steps the laser power. How does it affect my component? And then test against what is happening inside my object. So is the microstructure still okay? Is the mechanical properties okay? Is the surface roughness okay? Is my part still meeting specification? Once you have identified your process limits, your authority or regulated body needs you to have control mechanisms in place to ensure that those are safe and sound. What those varies and typical limits are is of course determined during the performance qualification. And so after you have controlled and varied all those possible variations and understood the effect, you lock the process parameters. In Smart Fusion, authorities don't like really that algorithm within the system is constantly modifying and changing the process parameters such as the laser power. So for them, it is absolutely critical that it's understood what the process variations of Smart Fusion have an effect on your product. But once this is understood, authorities can accept that a system is not having constant powers, but it needs to be controlled and locked after the process has been qualified. So why is freezing process parameters crucial after the qualification? So let's understand how additive manufacturing in powder bed fusion is actually working. You need a certain energy to melt material from its powder state to a liquid state, so to say, to solidify and your component, of course locally. However, the thermal conditions are constantly changing. So depending on the overhang angle, depending on whether support structures are available or not, the thermal conditions or site conditions are constantly adapting. So having constant process parameters such as fixed laser power, scan speed or hatch distance is not really representing of the true physical behavior or nature what happens in additive manufacturing. But of course we have, against this stark contrast, the needs for regulated industries that authorities can understand and control those modifications to your process. So it's absolutely vital that after you have understood how local process changes and modifications are affecting your properties, you need to lock those down, that you can ensure and be safe that your product that you've just manufactured is meeting its intended use.